All right. Okay, so I'm going to get started. Let's talk about the new homework assignment first. As you know, the exam is being passed around. It is one of the most, it's one of the favorite things that you guys like to do is recursion. And it's factorial. It is factorial. Now the program is already written in C. In other words, you can run it in C first, and then you work on the assembly version of that. Okay, so you can at least see how it operates. The main program is not something that you have to turn in assembly, so the long part of the program is nothing for you guys to worry. Okay. Even though some of you may want to know how it works. Okay, so when this program runs, it will take one parameter. So when you run the program, you say /factorial, and then you give it a number, and it will find the factorial of that number on the command line and print it out. The factorial of blah 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 is blah. Okay. So for those of you who don't know or have never seen ARGC and ARGV, this is a good chance to take a look at the argument count and also the argument array, so that you can learn how to use the command line options. The key is this particular part here. This is the only part that calls factorial. And your job is to implement factorial in assembly language. But I don't know what is factorial. That's fine. It is already done here. And all you have to do is to translate that into assembly. Are there any questions at this point about the nature of this particular homework assignment? This is one of the easier logic to translate. Because it only has one conditional statement. The condition of the conditional statement is only comparing against 0. We are not comparing, greater than or less than. It's just whether it is 0 or not. So that makes it a little bit easier. Got questions? Nope. Okay. Let's take a look at factorial. We should be able to do everything. Let's start with the reference of the parameter here. Do we know how to access the only parameter in this case of this subroutine? Yes. You have to do it, as a displacement from where EBP points to. So you have to use EBP for these programs because it's just a practice, a warm up for the next homework assignment where you have to use EBP, for local variables, parameters, and so on. Do we know how to compare a memory operand to 0, which is a constant? We know how to do that. Do we know how to implement a conditional statement? Yes. Okay. Do we know how to return a value of 1?
No.
Yeah, we do.
I remember it. Okay.
EAX. And the only part that may be a little bit tricky is this part here. Well, let's break it up into several parts. The return part is easy. Whatever you put into EAX is the return value. Okay, so that part is pretty easy. The only part that is difficult is how do I use I-1 and pass it as a parameter to factorial again and then call it again? Well, what do? You push the argument on the stack and then you call the subroutine. Yep. That's it. So what you need to do is to figure out what is I-1, push that on the stack, call factorial. When factorial returns, you have to clean up the stack because the parameter is still on the stack. Just clean up the stack, add 4 to the stack pointer, and you'll find the stack should be balanced at that point. You grab EAX as the return value of factorial. You multiply I to that EAX. The product becomes the value that you want to return, and so you put it into EAX. And if you do it right, using the mul instruction, MULL instruction, the product is already in EAX. So if you do it right, there's really not a whole lot of lines of code that you have to deal with in this program. Okay, but it serves as a practice, so that you can get familiarized with how to write subroutines in assembly. Are there any questions? No questions? And there are only a few more things to talk about here. If you use EBX, ESI, or EDI as registers in your subroutine, as the subroutine or the callee, you are responsible to save and restore those registers. So in this way, they're kind of like EBP. The callee is responsible to save and restore the registers, And this is basically just how compilers make use of the registers. So there's no particular reason why the callee is responsible to save and restore these registers. It's just that the caller assumes that. Okay, but you can avoid the use of all of these registers in this particular subroutine. It's not difficult enough that you will need a lot of registers. You can still use register EAX. You will definitely use EDX. And between EAX and EDX, you should have all the registers that you need. And the stack. The stack is a very useful place as well. Yep.
I had a question. So if we're implementing that subroutine, can we, instead of, how we have those global variables, can we, instead of pushing the actual values when passing them, can we push the address and use like the location in our assembly program just to access the variables that are written, that are compiled in C?
You cannot, because the call from C assumes that the parameter is on the stack already.
What about, like, let's not just say like a different program? Can we do like pass an address? Like a C creates a variable, right? And somewhere in memory, and then during sometime in C we want to call a subroutine that's written in assembly. So instead of pushing, like, we can also push prior to, because you say subroutine pushes that value on the stack, but what if we push prior to that the address of that variable? Would we be able to access it from assembly?
You can pass the address of something in C, right? Because in C you can have int asterisk I, which means I is a pointer to an integer.
Yeah, but
you can do the same thing.
In assembly we can find that on the stack if we get the address.
That's a good question. Let's think about it. Okay. So what he is asking is something like this.
This is a pass by value.
Pass by, he's asking about passing by reference.
Right. In the program is a pass by value.
Correct. In this program, we are only passing by value. There's no need to pass by reference. But what he's asking is, how do we pass by reference? Is that kind of the question? Okay. Let's take a look at what you just talked about here, and I'm going to use Notepad. Yeah, Notepad is fine. Okay, let's look at a very classic subroutine that you have to pass by reference or pass by pointer in this case. Swap, right? So in swap you have two pointers, and let's just say that we want to swap two integers in this case. So you have the first pointer pointing to I, and then you have the second pointer pointing to J. And we want to swap whatever these two pointers are pointing at. Okay? The C code to do this is really easy. The C code to do this is you need a local variable t as a temporary variable, and you use t to store whatever pi used to point to, and then you change whatever pi points to whatever pj points to, and then you change whatever pj points to t, which was the old value of whatever pi points to, and that's the sequence of swapping two integers. Are we doing okay so far with the C code? So everybody gets this, get the C code part? Okay. The question now is, how do we implement something like this in assembly? Is that going to help explain, to explain what you were asking?
No, I was like, you would do the swap in the separate subroutine in assembly, but you have the pointers in C code. Like,
yeah.
You have them created right there.
Yeah. So basically what I can have here is I have a, let's say, this is what I call a stub subroutine, because it doesn't really do anything other than illustrating the concepts. So in the stub subroutine, I have my local variable x and local variable y. In order to, okay, let's make sure that they all have some reasonable values. So y has -6, doesn't matter what it is. So if I want to swap the content or the values of x and y, I can call swap to do it. When I call swap, I will be passing the address of x as well as the address of y as my two parameters. Okay. So your question is the implementation of the call to swap or the implementation of the swap as a subroutine?
Well, my question is, will that right there, $x, will that push an address on the stack?
Yes. Let's go ahead and actually implement this, okay? Because sooner or later we'll have to deal with this, so we might as well just move the schedule a little bit and deal with this one here. Okay.
All right, thank you for asking.
Well, I think we are at this point. We are ready to talk about this, so it should be okay. All right, so we're going to implement stub first. How do we implement stub in assembly? So the first thing is, okay, I really do not like mouse pattern at this point because I cannot do my regular expression thing. So I'll save it into today's folder and then switch to VI. You can see how VI is kind of addicting. So we'll call this swap.s, swap.c first. Get rid of this, go back to my command line. Now I can use VI.
Need a 12-step program.
Today is 4, 10. Okay. Much better. Okay, so we'll go ahead and implement stub first. Okay, so I'll yank these lines, go ahead and make my stub.s, which is my assembly code. Substitute the beginning of each line with # and space. Now I'm ready. So we start with .global. Now this part is also a part of your homework assignment because you have to remember to use .global to export the symbol so that the linker can see it. So don't forget to do this part when you do your homework assignment. So .global stub in this case, and then define .text stub. And I always immediately put a return here just in case so that I don't forget. Now using our current method, the first thing we do is we push EBP, which means the very last thing we have to do is to pop EBP. Now you can also see that when I write my programs, I don't write it sequentially. I always write it in a structural way. I begin a structure, I immediately mark the end of that structure. So this way, I don't have to worry about things like forgetting to do it. Okay. So the next thing I want to do is to define some symbols so that I can keep track of the stack. In other words, what items are on the stack and exactly where they are relative to where EBP points to. That's what I want to do. The first one is always the same, OEBP equals 0, because EBP as a frame pointer points to its own saved old value on the stack. Is that part okay? It's just, yep.
So at some point implicitly EBP equals ESP. Is that
Exactly
correct?
at that point, because that's the instruction that we need in order to do that.
When you're going to do that.
And then the end has a matching code to reverse the operation.
All right.
Okay. We also know the return address is right on top of that, so it's OEBP plus 4. The plus 4 comes from OEBP, takes up 4 bytes on the stack. We don't have any parameters, so there's nothing else to say on that side of EBP. We do have local variables. In this case, my local variable x, which is my first local variable, I would make this OEBP minus 4. This 4 is the size of x itself because I have to allocate after I push EBP, and that's why the displacement of where EBP points to local variable x is going to be -4 in this case. Y is 1 below that, so the displacement to y is going to be the displacement to x minus 4, and once again this 4 has to do with the size of y and not the size of x. Are we doing okay so far with this picture? Okay. So once we have all these symbols defined, we can go into the subroutine and start to allocate space for the local variables. There are two ways to allocate for your local variables. I usually just do this. Add L, Y, which is the last local variable that I allocate space for, and just add it to ESP. Because remember, Y as a symbol is representing the displacement from where ESP points to the local variable y, which is the last local variable that I allocated on the stack. As the last one that I allocated on the stack, it has the lowest address. At this point, ESP and EBP are the same because of the instruction before this one. So that means if I just add y, which is -8 in this case, to ESP, I just reserved 8 bytes on the stack. Uninitialized, but allocated. Is that part okay? Any questions at this point? Yep.
I
turns out the return address is after the parameter. So why you it's OEBP minus 4. So should that be outside the stack?
OEBP minus 4.
Yeah.
It's on the other side of the stack. Local variables are allocated from the callee or the subroutine that is being called. And they're allocated after we push EBP.
Oh.
So that's why they're below the old EBP. They're under, quote unquote, under old EBP. Is that okay? Any questions? Now, I do not need another instruction here. In other words, some people may say, well, why don't we do a subtraction here to reverse, this operation? There's no need, because when I move EBP back to ESP, that automatically restores ESP to the point where it is pointing to its own old value. Or ESP will be pointing to the old value of EBP, which is the only point where I need to restore to. There's no other place that I need to restore it to. Is that okay so far? Does everybody understand what I just said? Yep. Okay.
Bit of a question. So to understand, you push first the EBP onto the stack, and then you place the pointer to that line into it, right? So it's
I make a copy of the stack pointer. EBP becomes a snapshot of the stack pointer.
So it's kind of like remembering where you were, like a bookmark, basically. Creating a bookmark so you can go back
It's
to
more
that
like creating a fixed point that you're pointing at. So any further push and pop operations will change ESP, but they're not going to change EBP. The displacement to my local variables also will not change if I am only starting with EBP. And that's why I need EBP, so that I can have further push and pop operations, but without affecting the changes of the displacement, because EBP always points to the same place as far as this call frame is concerned. Okay. So now that I have allocated for my local variables, I can actually go ahead and implement the code. So here we can say x get 24. That's pretty easy, because 24 is a constant, and any constant can be represented by a immediate operand. So I just move 24 to x open paren EBP, because remember, x itself is not a variable anymore. It does not represent an address. It only represents relative to where EBP points to, where do I find x. And that's why you always use it in a based operand, where EBP is a base register, and you're only adjusting where EBP points to in order to get to the local variable in this case. Question?
I mean, isn't what it's already pointing at already 24, so why are we moving 24 to it?
It's not 24 because I just allocated the space. I did not initialize that portion of the stack. Okay? Because my assembly code is closely resembling the C code. The C code did not have initialization in the definition, so I'm mirroring that in the assembly code.
Okay.
So the next line is going to deal with the other variable, which has -6, and I just use -6 here and move it to y, and then now I have to call the subroutine. So here's the big question: how do we call swap? In other words, I need to push not the content or the value of local variable x and y on the stack. I need to push the address of local variable x and y on the stack. Okay. Now, since I haven't really talked about the LEA instruction, there's no easy way to do it. LEA stands for low defective address, which is a very handy thing to have. But it only exists in CISC architectures, because in RISC architectures we can always calculate the address using just a few instructions. Tell me again, where is x? Where is my local variable x? On the stack.
4 from EBP.
It's 4 bytes in -4. Okay, it's 4 bytes before where EBP points to. Okay, so is there a way to push that number on the stack? How do we do it? There's several ways to do it.
Push
push L. Let's see, it's 4 back, so 4. Or
How about we just push that? Now remember, we also have to push the parameters backwards. Last parameter pushed first. Now I know it's a swap subroutine. The order of the operands, the order of the arguments do not really matter. But since we want to mirror the C code as much as we want to push Y first, or the address of Y first. So there are several ways to do it. You can push $y, which is just negative 8 in this case, on the stack. Then you can do the calculation on the stack. In other words, you can then do an add L percent EBP to whatever I just push on the stack. So that would do it. You can obviously reverse these two. In other words, you can say push L percent EBP. In other words, you push the value of EBP itself on the stack first, and then you add long $y to whatever the stack pointer points to. Because paren ESP close paren, it simply says, oh, whatever I just push on the stack. And I'm just adding EBP in this case to whatever I just pushed on the stack, which is actually just negative 8. So as a result, what is on the stack after the add L instruction is the address of local variable Y. Are we doing okay so far with these two instructions? You can also do the calculation using another register, move it into EAX and then do all the calculations in EAX and then push EAX. But that takes up more instructions, and this one, you only need 2 instructions to do it. And then we can do the same thing with X, add L, percent EBP, ESP. So now we have both the address of Y and the address of X pushed on the stack. And it's just time to call the swap subroutine. After the swap subroutine returns, what else is on the stack after the call instruction?
Return address.
The return address is not there anymore because the return in swap will take care of the return address. So we have 2 other items on the stack right now. The 2 parameters or the 2 arguments are still on the stack. So do I want to pop it into something? Are they useful at this point?
no, because we're not printing here anything.
Exactly, they're not useful because they're only useful to the subroutine that we were calling. Now that the subroutine is done, I don't need those parameters anymore. So the easiest way to adjust for that is simply to add 8 to ESP, because I'm just adjusting the stack pointer back up to where it was, but I'm not doing anything with the values with these 8 bytes because they're not useful to me anymore. Are we doing okay so far with this code? Yep.
Just really want to make sure, why are we adding and subtracting this 4
Which one?
from the beginning?
Okay, hold on a second. Okay, so which line are we talking about?
4, 5, 6.
4, 5, and 6. You have to look at the stack first. Okay, let me use a mouse pad or a spreadsheet so that we can show what is on the stack at that point. So I'm gonna go to Office, use Calc. Okay, so what is on the stack? Let me just make sure that we understand this is the high memory address, and that part is the low memory address. Okay. From the caller's perspective, I have to push the addresses on the stack first, right? In other words, $y, the address of y is pushed on the stack first. The address of x is pushed next. And then I have a call instruction. The call instruction has an implicit push of the return address. So since I don't really know exactly the number of the return address, I'll just say return address on the stack. After the return address will be inside the subroutine. The subroutine is going to have, it's going to push OEBP on the stack. And then after OEBP is pushed on the stack, in this case, this is the swap subroutine. The swap subroutine has one local variable. At this point, we are ready to allocate for the local variable, which in this case is t. Where is EBP pointing to? EBP points here, right? EBP points to that location. So that means t, my local variable, is 4 bytes below where EBP points to, my parameters, the first one is 8 bytes from where EBP points to, and then the other one is 12 bytes from where EBP points to. Is that making any sense? And this collectively is called a call frame or invocation frame, because almost all subroutines would have some elements of this entire frame. Are we doing okay so far with the relative locations of the parameters, the return address, old EBP, and the local variables? The caller is responsible for this part. The callee is responsible for this part. Is that okay so far? I'll keep this one up when I go back and continue with this program. Stub is done. Okay, this is the entire stub subroutine. Let's go back to the C subroutine, and this time we want to deal with swap. Swap starts on line 1, stops here, and we'll try to implement it in assembly. So once again, the usual stuff, .global swap so that the label is exported to the linker. .text to make sure that we are putting our code in the code section and not in the data section. And then we have swap : to mark the beginning of the swap subroutine and the return at the very end, so that we don't miss the return statement. It would be a very bad thing if your entire program works just fine, and then for some reason you forget to put a return at the very end of a subroutine, and then it doesn't work anymore. So I always put the return in, just like this. Next, I want to define, the displacement to all my stuff on the stack. As I said, always start with old EBP, because that's where EBP points to, is its own old value. It is saved on the stack. That's always 0. Return address is 4 bytes after that. And then I have my first parameter, which in this case is PI, is return address plus 4. And then PJ, which is my second parameter, is PI plus 4. That's on the positive side of where EBP points to. On the other side, I have my local variable T, which is 4 bytes below where EBP points to. So this would be old EBP minus 4. Is that okay? I mean, does this picture kind of resembles what I have here in the spreadsheet? Okay. So with all these constants defined, I no longer have to make any distinction between local variables versus parameters, because I just have to use the base operand using EBP as my base register, and I can access both parameters and local variables this way. Yep.
I wanted to make sure this old EBP and return address, are they like built-in functions, like a keyword by default, or
Which one?
return address and old EBP?
Nope. They're basically they're symbols. They're no different in terms of being symbols. They're no different from L1, L2, and all the other labels that we have defined. I just like to use these names consistently so that when I need to calculate the displacement to my parameters and local variables, I have a full picture of what is on the stack. Okay. And then we have a move L, ESP to EBP, and then we have the opposite here. So move L, EBP to ESP. And here we also have to allocate for one single global local variable. So we have to add L, $T to ESP, and that reserves the space for my local variable. Are we doing okay so far? This is exactly the same thing that I did with the other subroutine. So now that I'm done with all the bookkeeping stuff, making sure that we have OEBP pointing to the right place, reserving space for my local variable, we can actually go in and talk about the 3 instructions here. How would I do something like this? Well, first of all, what does this do? Move PI EBP to say EAX. Can someone tell me what is EAX after this instruction? Okay, I'll give you 2 choices. I'll give you 3 choices. Is EAX the address which is the same thing as PI in C? Or is EAX what PI points to? Or none of the above?
None of the above. You said two choices.
Well, I amended myself, saying that there are three choices. Yep.
It's needed.
Well, let's try to figure it out. Okay, what is this operand? Let me just go to this particular operand here. Okay, this operand is a based operand. It's using the base addressing mode. So, what is it? What is this operand? What is it specifying? It's basically saying go to where EBP points to. But hold on a second, not exactly that place. Let's add the displacement PI to the value of EBP, and that's the address where I want to grab 4 bytes. What exactly are those 4 bytes?
8 bytes away from.
Now those 4 bytes, but what is inside those 4 bytes?
The address.
The address is the address of an integer. So that means the first operand of this move instruction is actually a pointer. I'm copying the pointer to EAX. Is that okay? But according to the C instruction, I'm not interested in the pointer itself. I'm interested in what it points to. So that means I need one more indirect operation to compute the right-hand side of the assignment operation. That's not too hard. I can do something like this. This is a dereference, operation. Now that I have what PI points to stored in EAX, I can now copy that to the local variable t. In other words, I can now say move long EAX to t EBP. So these 3 instructions collectively will implement the C code which is above it. Are we doing okay so far with this? I think the key point is, what is PI paren EBP close paren? It is just the parameter itself, which is a pointer. I'm moving the pointer into EAX first, and then I dereference the pointer so that I'm grabbing the integer pointed to by the pointer, and then I copy the value of that to local variable t. Yep.
In stub, when we implemented stub, I don't think I didn't see or understand the point where the address of X or address of Y was put on the stack. Can you
Okay,
go
we
over that again?
can go back to that, but let me finish this one first. Okay,
Okay.
let me go finish this one. Okay, the next one is I want the right-hand side of the assignment is whatever PJ points to. I want to store that to whatever PI points to. So that means I can do about the same thing as the first one with the first instruction here, except I'm going to be a little bit tricky here. Instead of doing this, I'm not going to waste another register. I'll just push it on the stack. Okay? If I push this on the stack, then what I can do is to do something like this. I move the parameter itself into EAX again, and then I can do something which is which you can only do with a CISC processor, because with a RISC processor, you can only pop into a register. You cannot pop to where a register points to. But in this case, I can kind of do that because the Intel processor is a CISC processor. Is that okay? Does everybody understand this part of the code? Let me ask you one question then. What is on the stack after line 23? What did I push on the stack? Did I push a pointer to the stack, or did I push the content of pointed to by the pointer on the stack? The content.
Yeah.
The dereference happens first, and then we push that on the stack.
Which, maybe I've forgotten something, but going back to line 19, when we dereference the pointer there, is there a reason we have to put it into the register before we can pass it to the local variable? Or?
Yes, because if I put paren EAX, close paren in place of EAX here, now we have 2 memory operands. It is because of the restriction that we can only have up to 1 memory operand that we have to break it up and use a register to go between the 2 locations. All right, so the last one is pretty easy. We just have to say move L T EBP let's do it the other way. Use the stack. Push push the value of t on the stack, and then we want to compute. Then we want to get to pj. So move pj EBP to EAX, pop L to whatever EAX points to, and that should do the trick. Are we doing okay so far with this? Okay. This may be something that you might want to review because I did use quite a few tricks, so it's not very straightforward. There are other ways to make this more straightforward, but then I have to use up more registers to do that. I'm using the stack as a place to stash my temporary stuff so that I don't need to use up a register for that. Okay. Yep.
So with the push L T EBP line 27, you're actually pushing the address of.
No, I'm pushing the value of my local variable t on the stack. Because t is really just an integer. It is not a pointer to an integer. So when I push t on the stack, I'm pushing the value on the stack because t was never a pointer to begin with. Okay. All right. So let's go back to stub.
Don't we still need to move the stack to erase the local variable, or?
Yep, we did. Because we copy the frame pointer. We copy the frame pointer back to the stack pointer. Basically, this is saying, whatever is in between, which are my local variables, are useless, and I'm just deallocating everything in one shot.
Oh.
Okay. So let's go back to stub to answer your question about stub. All right. So getting back to stub, these two instructions will push the address of y on the stack.
Can you explain how it does that?
Okay, let's see here. Okay, what is the address of local variable y? That's the question, right?
Right.
Okay, so instead of using these instructions, which is kind of tricky, I could have done it this way. I could have said, move y to a register, let's say EAX here, add long EBP to EAX, and then push EAX on the stack. These three instructions would have done the same thing as the other two instructions. But would this be better? I mean, is that a clearer answer to the question?
Yeah. I think I get how the first one works anyway.
You mean this one?
The hashtag one.
Oh, okay.
Yeah.
But do you see how line 16 to line 18 would do exactly the same thing as line 19 to line 20 would do? They do the same calculations and end up pushing the same value on the stack, except in one I'm using ESP indirect to do my calculations on the stack.
Right, and y is what ESP is pointing to.
Yep.
Okay.
So here's another question. Which one do you think is more efficient?
Probably the hashtag.
Yep, the hash one is actually more efficient. Even though it has 3 instructions, the actual amount of time for these 3 instructions to execute is faster than the other 2 instructions. Can anyone kind of comment on why that is the case?
Let's push out.
Go ahead.
Registers are faster than the stack.
Registers are faster than the stack because every stack operation, push or pop, involves a memory operand that is implicit.
Right.
Okay? So when you look at line 19, even though the operand itself is an immediate operand, but because this is a stack operation, it is still a memory operand implied. Okay, so this has a memory write operation, which makes it slow. Okay, if you only have to work with the registers, it's really, really fast. But as soon as you have memory access, it slows everything down. And then the second instruction obviously is a memory has a memory operand because we have indirect ESP here. So the second so we have 2 instructions that are both using memory operands in the uncommented or line 19 to line 20. When you look at line 16 to line 18, how many instructions actually involves a memory operand?
One.
Only one, the last one. Only the push instruction has an implicit memory operand. The first two instructions has immediate operand and only register operands. So they are extremely fast. Only the push instruction is going to slow down a little bit. Yep.
This is a demonstration of the pass by reference.
Correct. It is pass by point, pass by address, because in C we don't really have pass by reference, but passing by reference works the same way.
And if instead of pushing the address of y on the stack, if you push the exact value of y on the stack, that would be example of pass by value. Right?
That is correct. If I push y paren EBP, that would be pushing the value of y itself, which is pass by value.
It's my understanding that pass by reference in C is more efficient than pass by value, and I'm not.
Only if you're dealing with a large structure.
How come they seem the same?
Because a pointer is also 4 bytes. Y itself is 4 bytes. The address of y is also 4 bytes. So if you can choose between those two, it's a toss-up in this case in terms of how many bytes you're using on the stack. But passing by reference is inefficient in a way because you need to dereference once in order to get back to what you need to access. But when you pass by value, when you get to the parameter itself, you get the value already. So that's why in this particular case, well, in this case, we don't have a choice because the swap subroutine needs the address in order to change whatever the pointer points to. But if you had a choice and you have a choice between passing an integer by value versus passing an integer by reference, passing by value is faster, is more efficient. Now, if you have to pass a structure, then there's a whole different story because the structure can have several hundred bytes. Passing by reference is only using up 4 bytes on the stack because it's only the address to the first byte of the structure. You're only using up 4 bytes. Passing by value means you have to copy several hundred bytes on the stack. The copying itself is going to take up a lot of time. Yep.
It seems to me like if you're doing this entirely in assembly, you can use labels to expedite the process. Like you'd have less memory operations if you could have a label pointing to something. Is that true?
But the whole point is we also want to have your assembly code or your subroutine written in assembly to interoperate with your C code.
Yeah, I guess I'm wondering why the C code doesn't do something like that.
Because that would use global variables like encapsulation, which are described as effective global variables.
Okay.
And global variables are evil.
Evil.
But they sound more efficient in this case.
No one's saying they're less efficient.
Then you'd only have
You
to have
don't want
one
to
copy
sacrifice
on the stack.
efficiency for
Evil.
yeah. That's why global variables are so bad because certain things are bad, but they're also very bitter at the same time, so people won't eat it. Certain poisons are. I mean, okay. Think about this. Okay, this is. I know this is getting off track a little bit. Think of ammonia and H2S, which is hydrogen sulfide. Okay, rotten egg smell. Okay. These two gases are poisonous gases, but how many people do you find would get killed by either H2S or ammonia? Almost none. Okay, because one, the toxicity is really low. You need to breathe in a lot to die, and two, it will probably be noticeable even when the amount is a trace amount, way before it becomes toxic. How about carbon monoxide? Carbon monoxide, can kill pretty easily because it's not detectable. Global variables are even worse because global variables smells even nice. So you would even try to, oh, that smells good. It's kind of like the flux of soldering. It smells good. So you would try to breathe in some more, and then that's bad. Yeah.
I know I'm getting a little off track here, but in C language, you don't have structures like for loops and while loops. Not in C, excuse me, in assembly language, you essentially have various go-tos. But the C language includes extra syntax to provide extra protection.
Yes.
It seems like there could be a way that the compiler could worry about the global variables and have all the efficiency, and then the C programmer would be unable to abuse it.
But this is efficient too. I mean, your compiler compiles to code just like this.
Yeah, but if you have for example, in recursion, if there was, if you could patch the address in and then
Wait, pass the address of what?
if you could create a pointer, and a label, and that label would indicate a position on the stack, and use that label, you'd only have to make one copy of a variable at all, and you could use it at any.
No, you couldn't.
Maybe, I don't know.
It wouldn't work.
Maybe I'm a little lost in my own head, but it seems like, I don't know.
Now recursion gets into the area where you cannot have a shared local variable or parameter across invocations. Okay, so in our head we have to make this very clear. Local variables and parameters are allocated on a per invocation basis, not on a per subroutine basis. Okay, does everybody understand what I just said? Because the difference is really, really subtle, but it's a big difference. When we say it's a per function or per subroutine basis, that means it is usually statically allocated. When you have subroutine F, and it has a static local variable, we just say, okay, this is the space for that local variable, and there's only one of them. When we say something is per invocation, that means every time you call the subroutine, a new version of that resource is allocated and created and be accessible. Local variables, auto local variables are like that. Every time you call a subroutine, you get a fresh set of local variables that are independent to the variables of prior invocations, even though they're still active. Parameters are the same way. When you want to do recursion, that becomes extremely important, that you have resources allocated on a per invocation basis and not on a per subroutine basis. There are languages out there that will allocate resources on a per subroutine basis and not on a per invocation basis. Almost all older languages like Fortran, COBOL, and so on and so forth would allocate statically allocated resources and not dynamically allocated resources like C and C++, Java, PHP, and so on. Okay, and those languages cannot support recursion. Fortran cannot support recursion. COBOL cannot support recursion. And that's why they have that limitation. Apple Soft Basic cannot support recursion. Yes, I said Apple Soft Basic. That was available for the Apple II, Apple IIe, and the Apple II Plus computers back in the late 70s and early 80s.
On the 64 and 128. What were they using on the 64 and the 128?
I do not know. But interestingly, Apple Soft Basic was also written by Microsoft. So there was a time where Microsoft and Apple cooperated.
Yeah, he didn't want to get sued again for monopoly.
But that's back when you had Go subs in Apple Soft Basic, and Go subs cannot support recursion because it only allocates one space to remember where to go back to. So recursion would not work in that case. Right. So are we doing okay so far with this stuff here? Okay. Is there anything left with the exam? Okay, I think somebody did not show up here. Okay. So do we want to talk about the exam?
Yes.
Sorry? Oh, which one? There's one more.
I got these back as soon as
Okay. So it has been withheld. There's a little bit of withholding here. Unintentional. Oh, I like this.
That's tricky.
I'm getting dizzy.
Yeah.
Oh.
Okay, let's talk about the exam. I know how much you guys do not want to talk about it, but I don't think it's as bad as you think it is, because I told students who asked me after the test, I might consider making this so that 2 questions out of 8 will be considered extra credit. So to get 100%, you only have to get 6 out of 6 right to get 100%. If you get 8 out of 6 right, you get extra credit, which overflows to your other test, final, or the homework assignment.
What happens at 7? What happens at 7?
Yeah, same thing. I mean, you have the extra amount to kind of spill over to another thing. All right, looking at question number 1. So let me go take a look at question number 1, and I will try to explain that using Let's see, VI, of course. Exam 2, question 1.s. Okay, so the code is G cos F, and then we have L3 here as a return instruction. F has a no op instruction to begin with, and then CMPL, some underscores for ESP, and then we have L2 with a return here, and then we have start, call G, and then we have L1 being the address of the no op instruction, and possibly some additional code here. All right, so that's the code in your question. The question is asking, what do I put in the underscores so that I end up with, let's see here, the Z flag being set. Okay, that's the question. In other words, what do I put here so that the Z flag will get set? Well, for this, in order to understand how this works, the best way to do it is to keep track of how the stack is being used when we're doing this. Okay. So what I'll do is I will attempt to do this without using a spreadsheet, and I'll start with the start instruction here. Okay. So at this point, we'll say that there's nothing on the stack. In other words, there is something on the stack, but it's not something that is under our control, and as a result, there's no way we can make something equal to this if that's what we are asking. Okay, so we'll just say that stack pointer is not, there's nothing on the stack at this point. Okay, okay, we call G. So after we call G, we'll end up at this instruction here, but at this point we'll have a return address on the stack. Does that return address have a label?
L1.
It's L1. Okay, so we have L1 on the stack, and I'm going to use this notation so that we can easily tell what is the boundary between the things. Call, okay, when we get to G, it's going to call F. So when we get to no op, what is on the stack? We have L1 on the stack, and then something else, and L3. Okay, very good. So L3 is on the stack as well. And when we get to this instruction, no stack operation has occurred yet. So we still have the same content on the stack right here. The question is, what exactly is the second operand of the compare instruction? Where is the stack pointer pointing to? Is the stack pointer pointing to L1, or is it pointing to L3?
L3.
The stack pointer is pointing at L3, but what is 4 bytes away from L3?
L1.
L1. So that means the same answer in the practice exam would also work here.
Yes. That's how we like it.
I had to really think about how to change the practice exam to this particular question so that I can still be asking about the same thing, but without making it too obvious. Because if I make this too obvious, some people will complain, go like, oh.
Well, there would be complaining. There'd be
But
congratulating, high-fiving me.
But is that okay? But does everybody understand the answer? Why the answer is the answer? Okay. All right, so that's the first question. We'll go ahead and take a look at the second question, x2, q2, s. And this one, this one is an interesting one. This one is an extra tricky one. Okay,
Did
we
everybody
have
get the same questions this time?
yeah.
Okay.
Awesome.
6A9E22. Is it D? Yep. Then we have a move 1 ESP to EVX. And then we have add L $4 to ESP, pop L EX, pop L ECX. All right. So here we have our program, and we'll do the same thing here, except in this case we have to do it in a byte by byte basis, so that it's easier to tell which byte is which byte. And I'm also going to do it in a way that is kind of counterintuitive, because high address will be on your left and low address will be on your right. Okay, because that way it's easier to grow the stack. Otherwise, I will have to pre-allocate and do it the opposite way. Okay, so when we push W 624, which 2 bytes are we pushing on the stack in what order?
From high end, it would be 0, 6, and then 2, 4.
Okay, very good. So these are all in hexadecimal. I'm not going to use 0x everywhere because they're all in hexadecimal. Okay, so now we have 0, 6, 2, 4 already on the stack, and now we have 0, 0, 6A, 9E, 2, 2. Don't forget the leading zeros. Okay, and now we have the DE, but don't forget the leading zeros too. So we'll go ahead and copy that. So we have leading 0 and then the DE. That's the entire content on the stack at this point. The stack pointer is pointing to the very last byte that we push on the stack. In other words, the stack pointer points to the byte with the content DE. Are we doing okay so far on the stack? This part is identical to the practice question at this point. The next instruction is going to copy 4 bytes because we have a move long instruction starting at the location that is 1 byte off from where ESP points to. Okay, so in this case, I will have to I'm going to do it this way so that we can just indicate which 4 bytes are copied. We know that this byte is the last byte that is being copied because it is 1 byte off from where ESP points to. Then we can also see that this byte is the last byte that we are copying. In other words, we are copying 6A, 9E, 2200 into EBX. Now, because we are listing high address on the left-hand side, the way you read this number does not need to be translated. The number is 6A, 9E, 2200 in EBX. So that answers the question. EBX is going to end up with, oh, okay, I need to comment this out first.
That's if you did IREA. EBX.
Sorry?
As a hexadecimal number.
As a hexadecimal?
You did IR, EBX.
Yeah, you can do that. 6A, 9E, 2200. Okay, so now we add 4 to the stack pointer. Now, if you add 4 to the stack pointer, you are effectively changing the stack so that it only has these 4 bytes left. And then we have a pop-out instruction. After this pop-out instruction, okay, there's nothing left on the stack. And EAX will get these 4 bytes, so EAX becomes 06240068. And now that the stack is empty, quote unquote empty, in other words, the known part of the stack is gone, so EAX is going to have question mark.
I mean ECX.
ECX.
Oh, ECX.
Yeah.
Just you can use many ways to tell me the same thing.
Yeah.
You can say ECX has a value that we cannot tell. You can say potential. You can even crash because if you are running out of stack space, this is beyond the room allocated for the stack. Potentially, you can cause it to crash. But anything along that line is fine. Just tell me that we don't know about this one. It may give us something, but we don't know what it is. Okay. If you get the first part right, EAX and EBX right, I'll probably just give you full credit already. So ECX is kind of like a little bonus thing.
It was mean. I reviewed that question 4 or 5 times to make sure I didn't miss something.
Took a lot of time.
Yep.
For the EBX, we don't have to think about the whole Indian. We don't have to swap it.
Well, I did not have to swap it here because in this case, high memory address is on the left-hand side. So the way we read it from left to right is already the value that should be in the register. So it has to do with how I list the content in memory in this case. Are there any questions at this point? No questions about this one? Okay, let's move on to the third one. Exam 2, question 3. Oh, this one, I like this one. Okay. Okay, in question number 3, I ask you, okay, at the line that is commented, some tricky code here, the subroutine determines that it needs to be called again by the caller. Specify the instruction that should replace the underline so that the return instruction, returns to the call instruction that called F to begin with, instead of the instruction after the call instruction. Okay, so I was being very specific of how this should be done. you can assume that the call instruction is 5 bytes long. Obviously, this kind of practice is very dangerous and brittle and should not be done at all in real life programming. So, all right. So that being said, in other words, we just want to adjust the return address by 5 bytes. So the instructions do it. Okay, first of all, first of all, we want to adjust the return address. The question is, what is the stack pointer pointing at that point where the underscore is? We are just about to execute the return statement.
Lowest byte of return address.
Exactly, it's already pointing to the return address. So that means, all we need is to say, well, you can use add L or subtract, doesn't matter which one. If you use add L, you just have to specify -5, and you just have to subtract 5 from where ESP is pointing at, because ESP is pointing to the return address already. All you have to do is adjust that to be 5 bytes, to be 5 locations earlier, then you would accomplish what the assignment or what the question is asking you to do.
I thought the call itself is 5 bytes wide, so I had to account for the return address plus 5.
The call instruction is 5 bytes long, but the return address is actually the address of the instruction after the call instruction. So if you want to go back to the call instruction itself, you have to subtract 5 to account for the instruction itself. Yep.
Why do you see add-on instead of sub? Is there any speed advantage or just preference?
Just preference.
Okay. I took this as it was being recursive because you said you would determine that to call itself again. So I pushed the 5 onto the stack, so when I hit return, it would automatically go back to that point.
If you push $5 on the stack, then it's going to continue execution at location 5 of your memory space.
I did push L5 with parentheses percentage ESP. So I pushed.
Okay. So what you did was push L5 ESP,
Yes.
like that. Okay. What that will do is it will copy the instruction that is 5 bytes away from the instruction following the call instruction on the stack. So it's copying the instruction itself on the stack, but not the address of the instruction on the stack.
Okay.
Yeah, all these indirect and base operands, can be a little handful sometimes. Okay, so are we doing okay with question number 3? Moving on to question number 4. I like this one too. Okay, this one is about, okay, let's do something to cross-check to make sure that the stack is balanced and it is proper before we do a return instruction. So instead of using some wrong value and crash and return to La La Land, we want to do some sanity check and say, is the stack at the right place? Okay, and the way that I did it is to use some random byte sequence or random 32-bit pattern as my signature, and I want to make sure that the signature is at the proper place before I return. Okay, so according to the instruction here, the prologue is I have a push L signature type of instruction so that I can push a bookmark on the stack, so to speak. The prologue requires a matching epilogue, which is the code after the actual code of the subroutine, to check the signature at the end of the subroutine. In other words, the end of the subroutine will look like this, some code that we have to specify, and then the return instruction. Write the code to replace this underline so that it checks whether the 32-bit signature is what the stack pointer is pointing at. If so, adjust the stack pointer as necessary and proceed to the return instruction to return normally. If not, which means if the signature is not there, then we want to branch to the label called stack exception. Okay, there are many ways to do this. Okay, we have talked about enough instructions that I can probably come up with 4 different ways to do it. Okay. All right, so let's go ahead and take a look at the solution, or at least one of the solutions. Okay, so at the beginning of F, we have push L 0x5 BE207A4. Okay, it doesn't matter what it is, you just have to match the same thing later on. Okay, and then we have a return instruction here. So presumably, right before the return instruction, the stack pointer should be pointing at the signature. In other words, the instruction also tells you that the code that you want to specify has to check whether the 32-bit signature is what the stack pointer is pointing at. So how do we do that? It's a compare instruction for sure, and it has the same signature, 5BE207A4. And what are we comparing against?
Yeah, because it was inside the ESP location.
What ESP points to, exactly. Not ESP itself, but what ESP points to. Okay, so there are only two possible results, right? Either it equals or not. I'm not interested in greater than or less than, I just want to know whether they are the same or not. If they are not the same, J and Z, I want to go to the label called stack exception. Is that okay? If they are the same, I have one extra thing to do before the return, because at this point, what is the stack pointer pointing at? The signature, right? It's not pointing at the return address. So if I try to execute return at this point, it's going to continue execution at location 5BE206A4, which is probably going to crash. So that means I need something to adjust the stack. Well, I can just do that using add4ESP. This is one way to do it. I can think of other ways to do it. If you can afford, now since I did not say that you cannot blow one register for the comparison, we can just pop it first, compare, and then do the branch. Okay? So the other way to do this is to pop it into a register first. Since I did not say that you cannot do that, well, let's go ahead and pop it into EAX. Then you can use the compare instruction against EAX, 5BE206A4, against EAX this time, J and Z to stack exception. And this time, I don't need to adjust the stack anymore because the pop instruction automatically adjusts the stack already. So that's fine too. That's another way to do it. Any questions about this one?
Why didn't you add 4? I'm sorry, I missed that part. Why didn't we add 4?
Because the stack pointer would still be pointing at the signature 32-bit and not the return address. So if I did not add 4 to the stack pointer, it would use the signature as a return address. But you did, this one has partial credit, obviously. I mean, if you figure out, portions of it, you will get partial credit for this type of question. Any questions at this point? Okay, let's move on to question number 5. X2Q5. All right, question number 5 is saying we want to observe the following code. Answer the question. At label L1, how does ESP compare to EBX? Express that as an equation. So I want you to tell me how those two registers relate to each other. I also want to know what is the value of EAX at label L1. So let's go ahead and write the code here first. Okay, move L ESP to EBX. Push L$6. Push L$13. Pop L EAX. Add 1 ESP indirect to EAX. And then we have L1. All right. Okay. I don't need a debugger to trace this code because we should know what is happening on the stack and the operations accordingly. So what I'll do is the same thing. I'm going to put comments next to the instructions as my trace on the stack. Okay. So at this point, okay, I need to think about how to represent this. Okay, this is what I'll do. I will just use EBX here to indicate what EBX is pointing at, which is something that we are not responsible for. Okay, this is not something that we push on the stack. And then we push the 6 on the stack. So 6 is going to be here. It is not pointed to by EBX because EBX is pointing to something that was pushed on the stack before the 6 on the stack. Are we doing okay so far? Now, because all the operations involve 32-bit operations, so I can basically just work with 32-bit chunks when I display the content on the stack. The next one is going to keep the 6 on the stack But in addition to that, we also have 13 on the stack. Then we pop EAX, from the stack. Okay, so that means the stack only has this left, but we also know that at this point, after this instruction, EAX is going to have the value of 13. Is that okay? Because that's what pop does. It will copy the value from the stack to the register, and then it will deallocate it from the stack. Are we doing okay so far with this? All right. At this point, we are adding. Oh, I forgot the L with the add. Okay. We are adding whatever the stack pointer is pointing at to the register EAX. What is the stack pointer pointing at? 6. So we are adding 6 to the register EAX. This instruction does not modify the stack or the stack pointer, but EAX ends up at 13 plus 6, which is 19. And at label L1, how does EBX relate to ESP? Well, let me see the question again. Okay, the question asked about the other one, the other way, which is ESP equals EBX minus 4 plus negative 4. There we go. So it doesn't matter how you specify this. For people, I think some people might have crossed the plus sign and changed it to a minus and then minus 4. That works. You specify negative 4. That works. If you want to specify the bit pattern of a 32-bit negative 4, that works with me too. Okay, quickly, what is that? 32-bit, the 32-bit of negative 4 in 2's complement. FFFF, FFF, C.
Sounds
Because FFFF, FFFF is negative 1. Okay, E is negative 2. What is before E? D is negative 3, so C is negative 4.
Yeah.
Did anyone specify negative 4 that way? No one? No one felt compelled to use 2's complement to specify that?
Next test.
Next test. Okay, question number 6. Question number 6. Evaluate the following partial code. Assume L1 and L2 are defined somewhere other than the partial code somewhere other than the partial code listed, and they are distinct. What is the range of value in BL that will make this partial code continue execution at label L1? Okay, so let me just put the code here first. CMPB 240 with %BL, and then we have JO, which is jump if overflow, okay, to L1, and then we have JMP to L2. All right. When you see JO, the first thing that should remind you is, it's signed interpretation. Okay, JO means we have to pay attention to the sign. The overflow flag is set when the sign makes no sense. Okay. All right. So the first thing we want to do is to look at 240 and say, okay, but what does it represent? What value is it representing as a signed 8-bit integer? Okay. So we want to take a look at 240, and let's see. We have to convert it into, well, there are 2 ways to do this. There are 2 ways to do this. You can use the 2's complement method. You can also use subtraction to figure out what is 240. Okay, I'll show you this little trick here. Okay, the 1's complement of 240 in 8 bits is 255 minus 240. Do you guys know this trick? No? I'm trying to do 2's complement without using binary numbers. But this works. This is 1's complement. We're not quite there with 2's complement, but 1's complement can be done this way. Well, let's try to figure out why this works. Okay. Okay, let's try to say, okay, 1's complement of 0, 1, 1, 0, 1, 1, 0, 1. What is that? That's a pretty easy one, right? We flip all the zeros to ones and we flip all the ones to zeros. So that's 1, 0, 0, 1, 0, 0, 1, 0. But would the subtraction do the same thing? In other words, if I do a subtraction like this, 1, 1, 1, 1, 1, 1, 1, 1, minus the number, the first one, which is 0, 0, 1, 1, 0, 1, 1, 0, 1, what do I get? This one is guaranteed not to have any borrows, right? Because we have ones on the top row. 1 minus something will never give you a borrow. So what do we get? 1 minus 1 is 1. 1 minus 0, excuse me, 1 minus 0 is 1. 1 minus 1 is 0, 0, 1, 0, 0, 1, 0. That's 2's complement. But what exactly is 2, 1, 1, 1, 1, 1, 1, 1, 1? That's 255. Okay, so this trick works. Okay, so now we have to do this, and which is this is 15, and the 2's complement is only 2's complement is 1's complement plus 1. So that means in this case it is 16. Okay, so that means, you know, this means 240 in 8-bit signed can also mean negative 16. Is that making any sense so far? So now the question is, what, you know, x minus negative 16 is out of range? Okay, add grammar here. So we want to resolve this. Okay, x minus negative 16 is out of range. The range of a signed 8-bit number is from where to where? Negative 128 to 127. Now x minus negative 16 is pretty much the same as x plus 16, has to be out of range. So what do you think x has to be? Well, first of all, x should be positive or negative? Positive. Has to be positive. Okay. So that means one end of x, okay, one end of the range is 127, because 127 plus 16 is definitely out of the range of 127. What is the other side of the range? The other end of the range is 127 minus 16 plus 1. Because if you just minus 16, then it is just barely representable using 8-bit signed. But if you add that 1 to it, then it's, you just push it out of the range. So that would be what? 112. Here we go. So the range is 112 to 127.
I got 113.
You got 113? If you write 113 or 111, I would assume that you kind of know how to get to the range, so you will get partial credit for 111 or 113. But if it is some other random value, then all right. Shall we move on, or do you think you guys have enough already? I got enough already. Okay. We can talk about this next Tuesday if you want to. I mean, there's no big hurry here. Sorry? Next Tuesday? Okay. Have a nice weekend. Work on the homework assignment. Sorry? Lazy.
I used the jump flag commands.
No, attention span. Attention span.
Sir? Yep.